So, you know, I use the Bluetooth, because if I walk away from the microphone over here, then you wouldn't be able to hear me. And now with my voice the way it is, I think you kind of need it. But sometimes this thing, you don't hear it, but I'm hearing in my ear, it'll say, phone 2 disconnected. I don't know why it's doing that, but sometimes it disconnects and it just won't work. And other times it works the whole time through. Right now it seems to be working. In first block today, I just had to record using this microphone and stay kind of close. We'll see how it goes. Now, this topic right here, function operations, it's in our textbook, okay? But it's in our textbook in a place that assumes that we've done some other things that we haven't done so far. So kind of the way our curriculum is set up and the way the book is, they really don't match up. So most of what I'm doing today is not coming from the textbook. The homework is going to be a handout that I'm going to give you. Just every time is just a little different. I mean, this book was published in 2007, right? Like, I don't know, like 8 years ago. In Hampton, we did two or three new Algebra 2 books during that time. But here, they haven't. They forego getting new textbooks in favor of raises for teachers last year or something like that before I was here. But, so sometimes we just have to kind of make do with what we've got. So this is the best I could come up with. So when we talk about function operations, the basic function operations are add, subtract, multiply, divide. Things that you already have some idea of. You've done all these things in other contexts, right? And if I gave you the examples here and said, okay, you just figure out what you're going to do, you'd probably do them all right, okay? There will be one other function operation that you will not know how to do. That is a new thing. But the basic function operations are still good for us, mostly because, especially when you get to divide, it brings up the issue of domain and the issue that we're supposed to start to get a handle of in this class, which is restricted domains. Sometimes what you plug in for X is limited. You're not allowed to just put anything in for X. And so we're going to see what those situations are. There's 2 of them right now that we should understand, and there'll be a third that we learn in this unit. So add, subtract, multiply, divide. That's what we start with. So when we say function operations, what it means is you're going to have more than one function, right? In this case, there's your f of x and g of x, both polynomials. And we're going to say, add them up. Now, when you see a problem that asks you to add them up, the notation could be like this. It could look like, in parentheses, f plus g, and then x. What that means is f of x plus g of x. So usually if it's given to you with this notation, you probably rewrite it like that. Okay, then if I had to just say, well, how do you think we're going to do that? What would you say? How will we add f of x plus g of x? No guesses? If that's f of x and that's g of x, how do you think you're going to add them up? Just add them up, right? Just add up x squared plus 1 plus x minus 2. I mean, just replace the f of x with what it equals, x squared plus 1. Replace the g of x with what it equals, x minus 2. I mean, it just literally means just add everything up. Yeah, combine like terms, put it in standard form. All right, What do you think it'll mean if we say f minus g of x? Nathan? To subtract them, right? Now, why will that be just a little more complicated than that? Peter? Right. If you're going to subtract, if this g of x has more than one term, you have to remember to distribute the minus, right? It'll affect everything. So either you take a step and you write it like x squared plus 1 minus parentheses x minus 2, and then you distribute. Or maybe you just do that second line as the first guess. And then combine my terms. Like that. So, and now the multiply, when you see the multiply, it could look like this. F dot g of x, which is going to be f of x times g of x. And, of course, we're just going to multiply. And that's a FOIL, right? What I got here? That's wrong. So add, subtract, multiply. Pretty basic. Just be careful when you do the subtract. You don't make a mistake there. Divide is going to be a little bit different, though. Okay. So let's say I'm going to divide f of x by g of x. Now, first, could we simplify that? I mean, you could do long division or synthetic division, but in the end, you'd still have a term that has a denominator you got to deal with. I went, again, I made all this stuff up, and my intent was not to make us do long division at this point. But this brings up one of our restrictions to the domain. You're not allowed to divide by 0. What happens when you divide by 0? Right? Nails on the blackboard, it doesn't work, right? You can't divide something into smaller segments it can reach 0, right? It doesn't work. If you put it in the calculator, error, right? Can't do it. So whenever you're dividing by a variable expression, you're going to have to make sure that there's not some chance that expression could equal 0. And whatever, if it could, you need to restrict those values of x from the domain. So what value of x would make that denominator equal 0? 2, right? The 0 of the denominator is 2. So when you state the domain, you have to say does not equal 2. Now, what it means is that x is a real number. It could be any real number, but it just can't be 2. Most of the time, you just say x does not equal 2. The rest of it is implied. Okay, well, I guess then it could be anything else. Yes, it can. Just can't be 2. So you are looking for the zeros of the denominator, and you need to exclude them from the domain. When you're dividing by a variable expression, you need to exclude the zeros of the denominator with a not equal statement like that. Now, what if we did the opposite? What if we did g of x over f of x? What is the domain? That? Let's see. He says x does not equal -1. How many say x does not equal -1? I mean, if x is -1, then x squared is 1, and the denominator is 2. That's not a 0. What are the zeros of the denominator? Okay? So there are no zeros of that denominator. Remember, we're only dealing with real numbers here. These are functions. We're talking about functions and graphs, right? And we can't graph the imaginary number. So if the denominator does not have a real 0, then it's all the domain is all real numbers. You can plug anything. That denominator will always be positive. Okay. So like this. X squared plus 1 equals 0. X squared equals -1. So x equals plus or minus I, right? So that is non-real. So domain is all real numbers. And I'm going to, just to save myself writing every time all real numbers, I'm going to use like a big fancy R, like that. So when it comes to a divide situation, you're looking for the zeros of the denominator. Okay. Jordan, okay. So the domain is the set of x values. That's the way you've learned it in the past, right? The x values are the inputs to the function, the independent variable, the thing that you get to choose what you're plugging in. You know, restrictions to the domain are just telling you you can't plug in everything. There's going to be some restriction on what you plug in for x. So the first one can't divide by 0. The second one is you can't take the square root of a negative. If you see a square root in your function, you have to say whatever's underneath the square root, you've got to make sure that it is not negative. Because if it's negative, you're going to get imaginary numbers again. Now the polynomial functions, like when we added and subtracted and multiplied polynomials, we got polynomials. Those are all real numbers. The domain's always all reals because there's no dividing going on. There's no square roots going on. There's no way to do either one of these things when you just got a polynomial. So we will see increasingly when you'll get a function defined, it may say after the function, comma, and that'll give a domain statement, something like x does not equal a number, or x is greater than a number, or something like that. Those are domain statements. They're increasingly from this point on, we see that kind of thing. Now, there's only one other restriction that we're going to have to worry about in this class. And really, I can't hardly think of anything else either. But that other restriction we're going to get to in this unit. And that's when we take logarithms, you can only take a logarithm of a positive number. We kind of saw that in that handout I gave you the other day, that one graph I said was a logarithm. And it didn't go on the left side. So you can't take a logarithm of a negative number. Other than that, those are all the restrictions to domain. Okay, I'm going to do this one. I think the next one will be for you, right? F of x plus g of x. Okay, so I added them up. The 3's canceled. I got 2x. What is the domain? So a function equals 2x. What's the domain? Is 2x a polynomial? Yeah, it's a polynomial. What do we say about the domain of polynomials? All real numbers. Domain, all reals. Okay, let's subtract. X plus 3 minus x minus 3, which makes it plus 3. So that's 6. And this one doesn't even have a variable in it anymore, but it's still a polynomial. It's a constant function, right? What is the domain? All reals. Okay. And multiply. X plus 3 times x minus 3 is x squared minus 9. Again, another polynomial. All reals. F of x divided by g of x. X plus 3 divided by x minus 3. What is the domain? Say again? Remember, what is the 0 of the denominator? What value of x makes the denominator equal 0? 3. So you have to say x does not equal 3. Right? Over here, it'll be the flip of that. X minus 3 over x plus 3. Now what's the domain? X does not equal negative 3. So you just got to keep that in mind. It could be more complicated than that in the denominator. I think one of the homework problems, there's a quadratic function or expression in the denominator. So you're going to have to see, does it have any zeros? If it has zeros, then you have to exclude them from the domain. Don't divide by 0. Ready? Okay. That's for you to try. So you can see the first three. Let me check if I made any mistakes there. Going fast. All real numbers for domains. What's the domain of f of x over g of x? What's the zero of the denominator? 1, right? 1 minus 1 is 0, right? So you're going to say domain is x does not equal 1. And how about this one? What's the not equal? 5 over 2? 5 halves. The zeros of the denominators. Okay. Sounds good. Okay. Now complicates things a little bit because now one of our functions is actually a square root. Okay, so now that brings up the other restriction to the variable for domain. Now, the easy part of this is that not a lot we can do to simplify x plus the square root of x. I mean, are they like terms? Can you combine them? No, you're done. But what's the domain? To make sure that we're not taking the square root of a negative, what's the domain of this function? I'll give you a hint. It's an inequality. You know, x, the domain is x greater than or equal to 0. Whatever is underneath a square root, you need to set greater than or equal to 0. I mean, this one, there's no solving to do. If there is a little bit of solving to do, then solve it. But take whatever's inside, set it greater than or equal to 0. Unlike the divide, where we're like excluding values, now we're using an inequality to say these are the acceptable values for x. Okay, and then the next one, x minus the square root of x. Again, no simplifying. And again, the domain is x greater than or equal to 0. X times the square root of x. No simplifying. X greater than or equal to 0. And f of x divided by g of x. What is the domain? Hint, it's not greater, x not greater than or equal to 0. What is it? What's that? X squared. What is that going to do? What's that, Peter? X is greater than 0, right? It can't be equal to 0 because you're dividing by that. Then you'd be dividing by 0. So then you'd have both things going on at the same time. So you need to say that x is greater than 0, not greater than or equal to, because it's in the denominator. Okay, what about if I flip those? Domain is, say again? Well, that would be for the denominator. You still got the square root. Got to deal with that. Can you take the square root of a negative? So from the numerator, we've got x greater than or equal to 0. From the denominator, we've got x does not equal 0. So now we put it together and we say x is greater than 0. Right? So you try that one. Okay, it's a little more, look at the f of x now. It's not the square root of x, it's the square root of x plus 1. So you need to figure out what are the values of x that make that expression 0 or greater than 0. So just look at the first one anyways. See what I did to find the domain. Take what's inside the radical, set it greater than or equal to 0, and solve. That's your domain. So you can see on the subtract and the multiply, I mean, you can't, there's no real simplifying to do between these things. Domain is still the same. All right. The f of x over g of x over f of x. Okay. Why is this one greater than negative 1 and not greater than or equal to? Because it's in the denominator. Yeah. Because of that? Well, we're going to get to this one. So I just did this. I didn't do the domain over here because this one gets to be a little more complicated, right? So in this one, we have no issues with the numerator ever. The numerator can be 0. We have an issue here because of the square root. This has to be greater than or equal to 0. Because it's in the denominator, it has to be greater than negative 1. X greater than negative 1. Right? Now, because of the square root in the numerator, we would say x has to be greater than or equal to negative 1. But what about the 2x in the denominator? Because of that, right, as Declan is saying, x can't be equal to 0. How do you put those things together? With the and? Yeah. I mean, just think of it on a number line, right? Here's negative 1, 0, and 1. Based on the numerator here, we would have to say that x is greater than or equal to negative 1, which means it would go from here and to the right, like that. But because of this in the denominator, you have to say that x does not equal 0, and that's right in the middle of what we just shaded in. So actually, the domain has got to have a little open circle there on 0. So it's really both of these. X is greater than or equal to negative 1, and x does not equal 0. They both come into play. I mean, there's times when you can get it the reverse of that. Like, what if I had one, not this one, where it said x is greater than or equal to 0, and then because of the denominator, x does not equal negative 1. Okay, but it was already greater than or equal to 0, so I don't have to worry about that. Here you do, because that point is still in that area. Okay. So I think we're going to skip that one. I think we did enough of that. Okay, now we get up to composition of functions. Okay, composition is not a basic function operation that you might have something that you remember from before that you used to do. It's a new operation, and it even has new notation, although you can write it with old notation if you want. The notation for a composition is actually, you write the f and the g for the functions, and then there's like a little open circle in between them. It's not an O, right? It's not the letter O. It's like the degree symbol that's just brought down in between the functions. Okay, that's what composition is. You don't want to look at something like that and think they mean multiplication. They don't mean multiplication. That would be a dot, right, to mean multiplication. Now, most of the time, if you're given it like this, right, then it'll be rewritten almost immediately as this, as f parentheses g parentheses x, right? Now, and that's all kind of function notation that we've used before. We never did one function inside of another, but we have used function notation before. Now, whether or not it's written like this or like this, the way you read it to yourself is f of g of x, right? F of g of x. I mean, to me, I always look at that little thing like a of, you know, f of g of x, f of g of x. You know, if there's any confusion, I mean, I think last class somebody asked about this too. You got to remember, function notation, even though we're using parentheses like this, right? That's not a multiplication. There's no part of this that says anything about multiplication, right? Function notation is just saying, you know, we have a function rule that tells us how this expression on the right leads to the y values associated with it, right? And you can't separate out the function letter and the x. They go together, right? And it's not a multiplication. I've seen in the past where I had like an f of x equals something, and then somebody like tries to divide by f in order to solve for x. You can't do that. You can't separate the f from the parentheses x. It's all together. And this is function notation here. F of g of x. Okay. So either way you want to write it, you know, you read it like f of g of x. So you could see that this g of x is inside the parentheses that goes with f. So I would call the g of x as an inner function, and the f of x is the outer function. This is called composition. So I'm going to do some composition, show you how they work. Right? In the end, they can be pretty easy in the end. So usually if you're given this new notation, right, you're going to take a step and rewrite it with the f parentheses g parentheses x. About half the time I'd say they don't even start with that. They just start immediately with the f of g of x. Either one's a composition. Come on. Okay, so rewrite it if necessary, and then replace the inner function with what it equals, right? G of x equals x plus 3. So rewrite it like this, f of x plus 3. Right? Replace the inner function. Okay. Now we've got f of x plus 3. Well, here's our f of x. F of x equals x squared. Okay, you've evaluated functions before. How do I find, if f of x is x squared, how would I find f of 2? What would you do? How do you find f of 2? We plug the 2 in for x squared, right? How would I find f of 5? I plug in the 5. What do you think I'm going to do to find f of x plus 3? I'm going to plug it in for the x. Okay, whatever is in here goes here, right? So I think I find that this is as good as any way to show this. But you're going to take this x plus 3 right there, and you're going to put it in the place of x there. So it looks like this. X plus 3 squared. right? That's the composition of functions. You put one function inside the other. Now, x plus 3 squared, we could definitely simplify that. Yeah, what if I reverse the order? Now I'm going to do g of f of x. G of f of x. I'm going to change color. Okay, that is going to be g of x squared. So I replace the f of x with what it equals. Okay, now how do I find g of x squared? Nathan, you okay? Again, how would I find g of anything? If I said g of 2, you would put a 2 there, right? If I say g of x squared, you put an x squared there, right? You put one function inside the other. Right, so this will be this function is going to go inside that. Now what is that going to look like? X squared plus 3. Done. That's the composition of functions. Are they equal? Is g of f of g of x equal to g of f of x? No. So which property doesn't hold for a composition of functions? What property is it that says that order isn't important? Commutative, right? So there is no commutative property for composition of functions. Although sometimes they will equal each other, they don't always. So it doesn't have the property. I think it's up to you. So you try to do that.
Please excuse the interruption for a
I think sometimes this process of like rewriting it and then saying f of that and then trying to put it in may be actually confusing you somewhat. That if you just like do one at a time, f of g of x, draw yourself a little thing like this where you just show that goes there, right? 2 times 4 minus x minus 1. That's what that is right there. And then when you do the reverse of that, right, you're going to say 2x minus 1 and put it there. 4 minus 2x minus 1. You just put it in the place of the variable. So this one is 8 minus 1 is 7 minus 2x. This one was 4 minus negative 1 makes 5 minus 2x. Yeah, it's a fair number, get at least one of those right. Just gotta remember, just if all of this here doesn't help you, just try to do this kind of thing where you just show you're taking that and putting it in there, or you're taking, or the opposite. Now, the thing to consider here, I mean, domain now becomes an issue again. And it's kind of complicated when you do a composition, because in a composition of functions, right, this function, the f of x, it has its own domain, right? The f has a domain which is here, and it maps to a range which is here. But then, because it's inside the G, the range of the f function is actually the domain of the G function. So it all kind of ties together like that. Somebody asked me last class, when do you ever use this stuff? We use this stuff all the time. I mean, if something depends on something else, then you would say it's a function of that thing, right? And there's always like one thing depends on another, which depends on another, which depends on another. You may think you could model one relationship. You can model a lot of like the single relationships, but can you put it together into something more meaningful? And there's one word problem I remember from math analysis was something like this, where we had a function that related the number of bacteria in some sample of something, I forget what, related to its temperature. And then we had another function that described its temperature as a function of how long has it been sitting outside of the refrigerator. So you could see how one thing depends on the other. We knew both of those relationships, but ultimately then the number of bacteria depended on, well, how long did you leave it outside the refrigerator? So you tie them together with a composition of functions. So, I mean, there's lots of real world kind of scenarios, you know, where one thing depends on another. You know, how much money you make depends on how many hours you work. How many hours you work could depend on, you know, how much homework you've got, and so how much time you've got available to work, you know. So you put it all together, and I guess ultimately how much homework you've got is going to determine how much money you make. Makes sense. So what it means is that sometimes when we do these problems, there can be you can get asked the question of domain. And the question of domain isn't as simple as looking at the composition and saying, well, it looks like the composition is a polynomial, therefore all real numbers. No, it could be that the inner function, the thing that you've got to go through to get to the outer function, the inner function might have a limited domain, and that will limit the composition of functions domain. So for example, if these are my two functions, right, and I try to do the composition f of g of x, and I just wrote it in that way immediately, right? Well, before I do this, what's the domain of g of x? X is greater than or equal to 0. Well, no matter what the composition looks like once we simplify it, it can't have a domain which is any more than x greater than or equal to 0, right? Because you can't get into that first function, right, unless you're in the domain. Now, this one in particular is a very simple example of it, but if I do f of the square root of x, and then that means I'm going to take this and I'm going to put it in the place of x there, which means it's the square root of x squared, right? And the square root of x squared is x. Now, if you're just looking at a function, which is f of x equals x, and somebody says, what's the domain? You're going to say, all real numbers. It's a polynomial. But it's not, because actually the square root of x had a limited domain. Right? So you have to say, this thing has a domain x greater than or equal to 0, and therefore this has a domain x greater than or equal to 0. Right? The domain of the inner function limits domain of composition. I can tell you, I mean, I know that a lot of the things we do in this unit are you know, conceptually a lot more difficult than things we've done before. I mean, you may struggle with the concept of domain, composition of functions. I mean, all of it, and it just builds one after the other. It can be complicated. We don't have to do that much with this. I mean, we do one thing because it leads to another thing and not a lot else, you know. So we're doing this right now because next class we're going to learn about what are inverse functions. And we need to know about inverse functions because that's how we learn about exponentials and logarithms. I mean, those are all just explicitly referenced in the SOL, so we've got to do. There's more to this stuff that we could do and that you would do in math analysis. So we at least have to, bring up the subjects. I think I'm talking more about domain than I have in the past, but I could tell you that it's a subject that we struggle with all along the way. I could tell you where I came from, we did, and what I hear from the other teachers here is they do here too. And maybe this, a class or two down the road, you'll be the one who's absolutely the master of it. Okay, it's really just more of understanding than there's anything that hard to do. It's just got to understand the concept of it. So let's try. I don't even remember this that well, but so let's say I do the f of g of x. F of g of x. Well, first, how do I find the domain of g of x? It's a square root. Emily? Right. You take the x minus 1, whatever it is, and you set it greater than or equal to 0. As long as that's true, then you're going to get x values that you can take the square root of. So you solve that. X is greater than or equal to 1. That's it. That's your domain. Okay, now when I do the composition, f of the square root of x minus 1, I leaned on the keyboard. Again, that means I'm taking this thing here and I'm putting it in the place of x there. So that looks like the square root of x minus 1 squared plus 3. You see how I did that? I just put it in the place. I still have the plus 3 afterwards. I squared it. Okay, and now this is x minus 1 plus 3, which is x minus 2. What is the domain? X is greater than or equal to 1. Again, if you look at y equals x minus 2, that's a straight line. That should not have a limited domain. But because it's actually the result of a composition and the inner function had a limited domain, it has a limited domain. It's plus 2. I did that last class too. Senior moment. Okay. And most of the time, when you get these things like this, they're usually not going to say domain oh, this is domain. It just, when you see the function and it says comma, x greater than or equal to 1, that's them telling you the domain. That is a domain statement. So you look for that. Not going to do that. Now, the last kind of problem I want to show you is sometimes I would say that for our purposes in Algebra 2, just more than likely than not, if you get 2 composition questions on the test, one of them might be like what we've done up till now, and the other one might be like this, right, where they're not asking you f of g of x. They've actually got a number in the place of the x. Okay, and that can be a much easier problem, much easier, because if you know what f of x is and g of x is, you can just evaluate them. I mean, what is g of 5? How do you find g of 5? Just plug it in, right? So do it. See what you get, right? G of 5 is 5 minus 4, which is 1. Okay, so now you can replace this with what it equals. So now you're going to find f of 1. Okay, how do you find f of 1? F of 1 equals 2 times 1 plus 3, which is 5. So f of g of 5 equals 5. So alternatively, you could have found f of g of x and then plugged in the 5, but you don't really have to do that. You could just evaluate the functions that are right in front of you. You know, if this was all we were doing, you know, I think that'd be easy. This wouldn't serve you very well going to math analysis. I think you really do need to find some f of g of x and g of f of x. I think the way this is going to go, next class we're going to do inverses. And then after that we're going to do exponentials and logarithms for 2 days. And all you'll see, every step, it ties together with the thing that came before. I hope that's the end. Okay. No, it's not the end. I think you have a U try right here. Try to do that there. Try to find f of g of 1 if there's your f of x and there's your g of x. How many got that? 9/5? Piece cake? So, like I said, we started to address for the first time restricted domains. That's an SOL. And then we found the composition to functions. Okay, so we've done that part of it. Next, find the inverse. And again, we find inverses, and the thing we realize is that when you have a function and its inverse, if you take the composition of the two, they cancel each other out. Okay. And so the homework is going to be a handout. I'll give it to you now.